Hey, hello there. Today I'm talking about question 336, palindrome pairs. The question is as follows. Given a list of unique words, we want to find all the pairs of distinct indices ij, such that the concatenation between word I and word j, it's a palindrome. So these two words has to be concatenating in this order. The j's word comes after i's word. So ij is not necessarily the same as ji, so the order does matters. And the resulting string is a palindrome. Basically, it means that the resulting string has to be symmetric around the middle. So it's something like a TBBT, the Big Bang theory. So let's talk about how we solve this. If we solve this in the most straightforward way, we will just compare all the pairs of words and physically concatenating those two together and do a linear pass to check for a palindrome. So the total runtime for this will be n squared multiplied by L. N is the number of nodes, number of words. So when we compare all the possible pairs, it's n squared. And the L is the linear pass to check for palindrome. That's linear with respect to the size of the word. So that's the brute force solution. The redundancy in this brute force solution is that let's say that if we have word I to be ABCD, the choice for word J, we will really never consider something like a LLS and S or SSSL. So we don't really want to actually do this concatenation and do the linear scan. We can identify those very early on because remember the palindrome is symmetric. So if we have A to be the leftmost character, the rightmost character after the concatenation has to be A as well. So if we enumerate over the prefix for the first word from left hand side, and we enumerate over the prefix in the reverse order from the right hand side choice, those two prefix has to match. If the two prefix does not match, then we don't have to consider anymore because it's already violating this symmetric relationship. So there will be three different scenarios when we do this prefix matching between these two words. One in the left to right order, the other one in the right to left order. It will be the two strings, the two words are of the same length. If we do the prefix matching towards the end of both words, since that they have the same length, it's basically TB and BT. So the two together can form a palindrome. The other situation is that the word on the left hand side is a little bit longer. So it will be TB something finish the left side word. The right hand side word is BT. So the extra part on the left hand side is very important. If the left hand side has a residual part, that's a palindrome by itself. We can still have those two words concatenating together to form a palindrome. It's the same story, similar story with the case where the right hand side word is longer. So if the right hand side word is longer, we want to test that the residual part is a palindrome or not. If it's a palindrome, the two can still be concatenating together to form a total palindrome in the end. So that's going to be the three different cases when we do this prefix matching among these two possible choices. So since that we're not talking about prefix matching, one thing very common data structure to use is prefix tree. So let's say that we actually generated a prefix tree. We got some nodes, the root. Let's increase the size a little bit. And we have a TB here. But it's not the end of it. After TB, we have a maybe something like A and another pass, CC. So if we consider a query word, that's basically BT. So now we are looking at the case where the choice for the left hand side has some extra stuff. So the BT is the choice for word J. The pass inside the try corresponding to the choice of word I. So we do this prefix matching. in the try we're from left to right basically. In the candidate search term choice word J we're doing the prefix from right to left. TB matches TB. So now we got a bunch of candidate words for word I that has some extra stuff. How we go about to figure out if the residual part is a palindrome or not? One thing we can do is to, once we have this matching from this node and on, we're gonna initialize either a DFS search or BFS search, probably DFS search, to test whether the residual path is a palindrome by itself. So here CC is a palindrome, A by itself is a palindrome. So we will basically try to find the end of word tag. In this case, it might be an indice, word indice attached to the node, and just to return that number with this indices for BT. So we will do a search inside the try to grab all the possible pairs. That would be okay, but it will be slow on the query. Actually, there could be something we can do in the insertion part that cause the insertion of words inside try to be a little bit more costly, but it will speed up this. You will get rid of the necessity to do either DFS search or probably DFS search. We will get rid of the necessity to DFS search on try every time that we have the prefix match. That is to basically annotate on every word from this node and on whether the residual part is a palindrome or not. If it's a palindrome, we just put an index, word index here. So the stuff on the node here is going to be the character. So the stuff associated with this node is going to be the character, the next character to node mapping, and the end of word flag, and also the list of words that from this node and on is a palindrome. So if we have that, once we have the TB and BT matching together here, we just directly read up all those indices indicating the word that would have a residual palindrome after this word. We just directly read out those index, pair those with the BT to return that. So that's the case when we have the string, the word on the left hand side that's longer. We can take care of them in this way. What if we are talking about the other case that maybe the search term is longer than the pass we have. Maybe we have TBA, ABT, and D. So we will do the prefix matching. We will match it until this node A. So it's even simpler than that case. All we need to do is after we match the TBA with TBA inside the try, we will just do a partial palindrome test on the residual part for this choice of the word on the right hand side. If the residual part on the choice of the right hand side is a palindrome, then we can form something like a TBA DABT. So that's the three different scenarios. The first is that we have an end of word at the try pass that's of the same size as the query term. The other one is that the pass contains some residual palindrome residual pass, partial pass after this node when we once we done the prefix match. The third situation is that after we done the prefix match, we exhausted one pass in the try, but we still have some characters, residual partial strings on the query term. Then we run a partial palindrome test on that. So that's pretty much the overall strategy. The runtime for this is going to be k squared multiplied L squared multiplied m. The L squared is basically the time needed to insert a word inside this try data structure, because it takes L time to insert the word alone, but we have to annotate those nodes here for that for to include all the word index where after this node it will be a palindrome. So the way we do it is basically when we insert a T, we'll test whether the residual part of BCC is a palindrome or not. Because it's not a palindrome, we don't put the word index after T. But once we inserted B, we want to test the residual part is CC. Since it's a palindrome, we insert a index number at this node B. Annotate that number here. So for every character we insert, we have to do another pass to check for partial palindromes. So that's why the insertion will become L squared multiplied by M. But the query part will be just M multiplied by L. For n different words, we want to try to follow the pass here and to do the thing. So use L squared multiplied by n to initialize the try, and M multiplied by L to do the matching, to do the pair to extract all the pairs of indices. So it's compared to M squared multiplied by L, this could be potentially much lower if we have n to be large. So that's the runtime analysis for this. So we're just gonna solve this with the just gonna try to code it up quickly. It's gonna be quite some code here. So we're gonna do a try node here. So that's the stuff that we put on the try node. You know, it's associated with a node value, a character value. It also keeps a character to child node mapping, which is we get that by subclass default dictionary. There are two other things, which is end of word flag, meaning that do we have an end of word here? So default value is false, and it also has a list of the word index that from this node and on, excluding this word, excluding this character, but the residual string after this character of the word is a palindrome. So we're gonna call this word index. So it's going to be an empty list. So that's the try node. Just going to initialize this data structure. Oh, sorry, we can do that in the in here. So we create a root node. Just going to lay out the code here. It's going to break into two different sections, and here is the populating the try. And the second portion is going to be finding the pairs. So we're going to do the populating the try first. So we definitely want to advance more into the try, and after we insert the word, we will flag the word to be end of word. But every time that we inserted a character, we want to test whether the residual part of the word is a palindrome or not. So if the word from this J's location and on, it's a palindrome, we will annotate that onto the node. Oh, sorry. I should use a word index here to indicating it's an end of word. It's the end of word I, word index. So default is -1. So I'm doing. And the list here, the indices list is the index for the word after this try node. It will be a partial palindrome. So call this list for lack of a better name, I guess. Yeah, so that's the populating of the try. The only thing that's different is that we put this annotation here. We have a list of all the words after this try node character will be a partial palindrome. So let's code this here. Did I misspell this? Palindrome. Ah. Just gonna call it word and left. So the thing we do is to grab the right hand side, which is the very last character in the word. While this two pointer hasn't met in the middle, we want to increment and decrement those two and just test whether it's symmetric or not. Otherwise, if we successfully meet in the middle, it's totally symmetric, so we return true. So this partial palindrome is testing the word from the else index and on. So that's what we've been using here. We insert certain characters and just annotate from this character and on. The remainder part is a palindrome. So that's what we put on the try. Then it's the find thing. So what we're gonna do is to for I word in the words, let's move this thing up to have some more space. For every word we want to do a try search. And so notice that when we do the prefix matching for the possible candidate on the right hand side, we are doing that in the reversed order. So we reverse the word and enumerate over that. So the thing that we want to test is if we have a break of the symmetric. If the node, the try node, has the value does not have the character, or if the node is if the character is not in the try node, it's not a children for the try node, that means we have already violated the symmetric requirement. So we can ignore this word possible candidate on the right hand side altogether. Otherwise, we would just advance one more time, move on to the next node. One thing we need to check here is that if we have a word ending here, that means on the left hand side it's already exhausted all the characters, but on the right hand side it's just a part of the right hand side, but we have some more stuff like the search term is TBAD, and we have TBA, and there is an end of word flag here, meaning that we want to do this residual part of the search term to see whether we have a palindrome or not. So that's the third case I talked about. So let's point it here. If case 3 query is longer than a possible so j is longer than a possible word I. So that's indicative by that the word has an index that's not -1. And we do this partial palindrome test for the candidate reversed word from this current location and on. If that's the case, we find the TBAD, we find the TBA DABT. So we put this onto the result. We just call this pairs. So the order for this is that the words index, the try-pass is on the left-hand side, and the right-hand side is this J. It's this I we're looking at, the query, the index for the queried word. So that's the try search. So if we don't break, that leads us to the other two cases. So the first case is that the TB end of word and BT case. That's that means the node after the first node inside this else condition here would be a node that has a word index that's not -1, that's not I. The reason we check for I is that if we have something like AA, the search term is also AA. We don't want to have that duplicate. So the condition is that if node.word index is not -1, or it's also not I, then this two has to form a pair. Otherwise, not otherwise, just resuming from there, we want to test, we want to basically combine all those words where we have the residual part to be palindrome as well, to pair those with the query word to form a pairs and push that onto the pairs. So that would be extend all the pairs. The nodes were the try pass is always going to be on the left. Oh, sorry. So it's the right hand side is always the query, but the left hand side is the stuff on the list. Let's just call it how do I do this in a more Pythonic way? Map node get item and no, sorry, it's more complicated than I think. I'm just going to enumerate over all those. It's pairs of nodes. Yeah, that's it. That should be it. So just gonna quickly note it here. Case 1, word I is equal to word J, totally reversed together. They have the same length. They perfectly mirroring each other. That's taken care of here. And all the rest of the cases here. Word I is something like ABC with palindrome SOS, and word J is the query term is something like CBA. All those cases will be captured here. So that's that, and we return the pairs. So let's see if it works. I'm just gonna read about the code to see if we have problems. So that's the try node definition. We subclass the default dictionary because we want to use the child, the character to the next character to the child node association. We have a word index indicating whether it's an end of word of the ice word. The list is the word that from this character and on, the residual string is a palindrome, partial palindrome. So here is the definition for this helper function to test whether the residual part of a string is a palindrome. From else location and on, we just check for the symmetric property between the leftmost and rightmost one and try to move them together to the middle. So that looks right too. Here we initialize this try and try to populate in the try. Here is the enumerate. For every word, we enumerate over the index and word. We start a new traversal inside try from the root. For every character in the word, if it's not a node inside try, we will create that node and establish the character to child node association, and also just advance through that newly created link. But before we do that, we want to test whether the residual string for this word from J and on is actually a palindrome. If it's a palindrome, we annotate the current node that hey, after me, the word I will contain a palindrome part. So if you do prefix match with me and terminate it at this position, this word I can form a palindrome with you because it's ABC. You are ABC in the reverse order, and the word I is ABC with some palindrome in between. So that the index on this list will help us to do this matching a lot easier. And after we finish the inserting of this word, we just put the word index onto the node. So that's the populating of the try. It seems okay. Then it's the actual finding part. We enumerate over all the words again. For every node, for every word, we initialize a try search traversal. The thing we do is to reverse the search time because we consider the prefix matching from the right hand side towards left hand side. So we actually physically reverse the word. And we enumerate over the word character by character. Here is that if the try pass is the end of word, so it's not -1, we want to test whether the residual part of the search word is a palindrome. So we're doing this partial palindrome test. If that's the case, that means the try pass is AB. The query term is AB SOS something if we read from right hand side to left hand side. If that's the case, we just put the try pass word on the left hand side and the query term on the right hand side. So that's this node word index and I pairs. We push that pairs onto the result. Here is the test if the symmetric testing between these two prefix already broke, then we exit this check. So otherwise we would just try to go to the next character, examine the next character. If we never break, that means we have perfect prefix match. There are another two cases. The first one is that if the node on the try is indeed a termination node, and it's also not a node that the same node as the I we're looking at, then we have a equal length symmetric matching. So we push this pair onto the pairs. Otherwise, we'll look up all the word that from this point and on is a small palindrome after that, and we push all those pairs onto the list as well. So that's that seems right. Let me try to run it. It seems okay. Okay, it's accepted, but quite slow. Wondering why. Is there any place in my code that's super slow? Anyway, I don't see that. I don't think anything that's suspiciously too slow. So that's one way we can solve this by inserting the word in the right order. But when we query, we do the reverse order. The other way is to insert those words in reverse order. And when we query, we have the word in the right order. I'm gonna just try to modify this real quick to change my solution to that. Because it's going to be quite important if we want to solve the follow-up to this question. So to do that, we will basically just modify a few things. We're going to comment it out and annotate the code. So for the population part, we're going to insert the words inside in the reverse order. So just going to copy this part here. And anywhere we have a word, we'll just change that into reverse word. Let me comment it. A little bit more comments. Yeah, you get the idea. I don't want to put more text because it's already very crowded. So we're going to enumerate over the word in the reversed order and check for partial palindrome in the reversed word, and do the same append, do the same traverse, annotating the word index the same way. But in the find part, we no longer do this reverse anymore. Just going to comment this out. So we actually, in the query, we do the left to right. And so for that reason, we have to change this as well. Let me make this a little bit smaller. I don't want line breaks. So it's going to be word. And now, since that when we insert the word as the reverse order and we query the word in the right order, we have to change the order we put this to index. It has to be I and node dot word index. The same thing. The rest should be the same for this for branch. In the else branch, do we need to change anything? Yeah, we need to change the order. We need to change the order we append the two pairs, because now the query terminal is on the left hand side. The path, the nodes inside the we can get from the try path is on the right hand side now. So this has to change in the other direction as well. We have to put I on the left, K on the right hand side. So let's see. So just want to make sure that I put the reversed word inside the population, but in the actual find I'm using the word. It seems so. So let's give it another try. It seems working as well. If we submit it, it's also working. So the difference beside this two is that the first one being commented out is that we insert word in the from left to right. So, but the second approach is that we insert word from right to left. The thing about this is that the possible follow-up is, what if this this data structure has to support online operations? So this add operation has to be its own function. We don't necessarily have the list of all possible words in the upfront, so there are new words coming in. We're still gonna populate the path inside the try for any given new words, and we want also support this query. So instead of enumerating over all the possible words, it's just going to be a single word throwing at us, and we want to look at can we form a palindrome with the words we have. Notice that when we push the pairs, in the first version, I is always on the right hand side. In the modified version, the query terms index, the query term is always on the left hand side. So, but thinking about forming palindrome, this query can be on either left or right, and we want to actually to return all of those possibilities. So just using a single try does not satisfy the online requirement. So we have to basically keep two tries. One is inserted in the normal order. The other try, the words are inserted in the reverse order. And to search through this different two tries, we basically just gonna have this commented version on one try, have this not commented version to go with the other try, so that we can make sure we have both cases where the query is on the left and the query is on the right. So have two tries will support the online requirement of kind of follow up to this question. So it's getting too long. I have to cut off the video, but you get the idea. I think you get the idea if you really follow this long. Alright, so that's the solution, and a brief talk about how we're gonna have two tries to handle the follow-up question. Okay, that's it for today.